Hello. In this session of Lab 11, we'll see about MQ135 sensor. The main agenda of this session is we'll see the story behind the MQ135 lab creation and what is that MQ135 module really is and what are the features and applications of MQ135 and how gas concentrations are mainly measured and what is the working principle and how it is dependent on the temperature. If you ask me what is the story behind actually creating this lab, this Xiaomi gas detector recently what I've seen in one of their YouTube page is the inspiration for that, where they use it for raising alarms for any gas leakage. So I just thought like why don't we create one gas detector which tries to give you out push notifications. So we are going to create a similar thing here. In the project we are going to create a push notification, and before that we have to learn what is this MQ135 sensor, and then we'll move on to create a push notification using push bullet. If you see the MQ135 module, basically it is a module which is having a gas sensor, and you can connect your voltage sources VCC ground, and you will have two outputs here, a digital output and an analog output. Digital output is essentially is coming from an operation amplifier, or in other words it's called as comparator in simple terms, where you compare the levels of resistance or the voltage drop and then you raise an alarm. This is basically a hard tuning, not a software tuning. There are two ways to use this module. You can straight away connect this digital module and see whether there is any alarm or not, but this requires a particular calibration. You have to see what is your threshold and then decide what to do. There is another technique where you use an analog output and take that, convert it into digital and see what is the thing coming, and based on that you can take a decision. This thing can also be done. So in this module we'll try to see analog output example rather. Mainly the features and applications are like you can use it in various applications of like a gas leakage detection, air quality detection, alcohol detection, whether there is any gasoline leakage detection, all these kind of extreme environments like coal mines. Also it can be used. Different kind of gases you can actually sense. If you go to the data sheet of MQ135, you will see it can detect or measure your NH3, NOx, alcohol, benzene, smoke, CO2, all these things. Now, coming to concentration measurement, usually when we are saying about measurement of gas concentration, we do it in terms of ppm, which is called parts per million. Parts per million is something like you have a million molecules or a million gas molecules, among which how many are your particular gas molecules are. For example, we want to measure CO2 in particular environment, and you measured something and you got it to be 1000 ppm. What it means is you have 1000 molecules of CO2 in the 1 million gas molecules. A gas is not just CO2. You can have an nitrogen, you have oxygen in it, you have carbon monoxide, carbon dioxide, different kind of gases. You have a little bit of inert gases, all these kind of gases. So the measurement, usual measurement which is used for quantifying the concentration of gas is parts per million or ppm. So if you see the working principle of MQ135 sensor, it basically has a variable resistance or resistor whose resistance changes with the gas concentration it has been subjected to. So in this diagram, if you see, you have biased the sensor and you have a load resistance. So you are trying to measure the voltage output across the load resistance, and you want to categorize based on the change in the resistance what is the kind of gas which I have detected. For example, if you see this graph, this clearly shows you, if suppose the gas is CO2, which has been shown here with the cross mark, the curve which is followed is this. So that means you will have a change in the resistance, a drop like this with respect to RO. This is an averaged value, RS by RO, where RS is the resistance of the sensor, RO is the resistance at 100 ppm of NH3 in clean air. So this is taken as actual reference, I can say. So concentration of 100 ppm of NH3 in the clean air is taken as the reference, R0, and RS is the sensor resistance at various concentration of gases. So if you see the normalized figures, so the values of RS by R0 vary like this. If suppose they reach a particular figure here to a particular value like this, which means greater than somewhere around 3 or 4, I mean the normalized resistance, then this corresponds to 100 ppm level of that particular gas. For example, if you take carbon monoxide CO, if my RS by R0 is almost equivalent to somewhere around 2, that corresponds to 100 ppm of carbon monoxide in the air, or the sensor is subjected to that much ppm of carbon monoxide. This is how we measure the gas concentrations using this sensor. And it is to be noted that there is a clear cut effect of temperature on this sensor. So the resistance that we are speaking about, it does not only change with the gas concentration it has been subjected to, but also changes with the temperature it is been subjected to. So always we have to perform the temperature compensation for the measured ppm of gas level. So let's go to the code.